Good morning. Well, my name is Ramin, and uh, I'm going to be with you in a couple of hours on this flow assurance modeling using Hydroflash. So first, I want to check with you all. Can you hear me? You can just unmute yourself and let me know if you cannot hear me. Okay. Right. Okay, so I'm here with Professor Bahman Tohidi. Bahman, do you want to say anything?
Good morning or good afternoon. My name is Bahman Touidi. I'm joining you from home because of this coronavirus. So my name is, I work at Hydrate University and Hydrafact Limited. Basically, I'm here to remotely take part in this course supporting Rami.
Thank you, Bahman. Well, as I said, my name is Rami Musavi. I joined Hyderabad University in 2012. I did my PhD in Institute of Petroleum Engineering. My area of study was phase equilibrium modeling and measurement of CO2 and brine system for CCS applications. And well, after I graduated from my PhD and did my Viva, I joined Hydrafact as a scientific software developer and flow assurance modeling flow assurance engineer. And since then, I have been responsible for development of Hydroflash or PVT simulation software. And also I'm responsible for modeling consultancy projects in Hydrofact. Okay, so I'm sure that you all have the course material I've sent to you. In the first section of the course material, you will find some information, some very general and brief information about wax, hydrates, and asphaltene, which are the main causes of blockage and flow assurance problems in the pipelines. And well, these are very general information, just if you want to have a look. And in section 2, here, we will have a case study. There is a blockage, and we want to investigate using modeling what was the cause of the blockage and how we could solve the problem and other problems that was associated with this blockage. So the problem is that an 8-inch pipeline was experiencing a blockage in June 1993. A survey using a strain gauge and pressure pulses from each end of the pipeline identified a blocked section of 2 kilometers long. Following conditions of the site is available. Water depth was 140 meters. Minimum seabed temperatures was 5 degrees. Minimum surface temperatures was 15 degrees. Minimum air temperature was -6. And pipeline internal ID was 171.1 millimeter, and pipeline length was 10,000 meters. And you know, these are the flow rates of the production and water produced. The pipeline was inhibited from hydrate formation by injected of 2.4 cubic meter per day, or 15 barrel per day of methanol. However, they were not sure if the pump was working properly. So zero inhibitor dosage should be considered in the calculations. To remedy the problem, the pipeline was depressurized at the downstream of the blockage and wellhead upstream of the blockage. These are the data and the pressure information of the pipeline on the downstream and the wellhead upstream of the blockage. And in table 1, you can find the composition of the reservoir fluid and the PVT information, GOR, molecular weights, and oil density, and also the SARA analysis of the oil, and also some measurements about wax content, saturation properties, and WDT. So the first question and the first part of the case study is that will pipeline depressurization dissociate all hydrates? So first of all, we want to investigate if the depressurizations of the pipeline will resolve the blockage. So Bahman, do you want to talk about this case study and give people some background about it? Bahman?
Mute. Okay, can you hear me?
Okay.
Yeah?
Yes,
Yeah.
yes, now.
This case came to us in 1994, and they had a blockage, and if you go back and look at the composition of the fluid,
Yeah.
if C7 plus, look at the C7 plus, please. Yeah, you see that C7 plus is 20.17 more percent. That is a light oil, because as you know, the C7 plus below 12.5 is gas condensate. So this is very light oil, probably a volatile oil, most likely is volatile oil. Now, volatile oil is very dangerous fluid because it can form hydrate, it can also would have very bad wax problem. Not as much on the asphaltene, but obviously you need to look at all possibilities. So they came to us after the blockage, and they initially wanted to know if hydrate has formed in the pipeline. So I suggest we go along the Rami presentation, and then until I intervene later to talk more about problem. Here, because they were thinking that because they didn't have the methanol injection pump, they have a serious hydrate problem. So I suggest you go a bit forward, and I'll come back to present more.
Okay, thank you very much. So, so we know the composition of the oil, we know the information, the pressures, the flow rates, and so the first of all, to know whether the pressurization dissociate all hydrates, we need to start modeling. So let me change my screen share. Right. So this is our software, Hydroflash. Hydroflash is Hydrafact, PVT, and thermodynamic modeling software, with more focus on flow assurance problems. And Hydroflash, because we work closely with university, we have tuned our model with the most reliable experimental data, and we work closely with our laboratory as well here in Hydrafact. So our model and our claim is that our predictions are very close to the real behavior of the system, and our predictions are very close to the experimental data of that system. So this is the main window of Hydroflash. Has 3 sections. The first section is this section, which you can see is the welcome page, and I can close this one. Everything, all the calculations results and the graphs, the sheets will be shown in this section, and this section is for features, calculations, database management. If you want to characterize a composition or create a composition, settings, and also help. So all these features and options are in this section, is the main ribbon, and everything, all the parameters of all calculations, input parameters, or some features or options you want to perform in a calculation, they all will be here in this section, in the parameter section. In Hydroflash, we work with databases. So that means that a user is able to create a database and store and save everything, calculation results, compositions, everything in a database. That helps user to organize the calculations and modeling very well. Because, for example, if you're working on 3 or 4 projects at the same time, and you don't want to mix all these Excel files and input files, so you want to have everything in one file, then you can create a database, then you can create the compositions and the results, and then you can save everything on a single database. And then whenever you want, you can back up that database, and whenever you want, you can import that database and use and see the results and use the compositions, and you perform the calculations again. So the first thing to start using Hydroflash is to create a database. As you can see, all these buttons here are now disabled because I haven't created a database. To create a database, we need to go to Database Management tab and press this button, Create Database. I call this February course, and then press Save. I give it a location, which is my desktop, and that's me done. So as you can see, the active database is now the database I just made, and now all these calculation buttons, they are now active, and I can start performing calculations and creating compositions. Or if you have created a database before, you can import that database. For example, I've created all the compositions for this course before, so I want to import it. I can select or browse the file here. So the course, and now the database is imported. So as you can see, now I have 2 databases in my list of databases, active databases. I can change the active database to the one that I changed, or the one that I have created before. Okay. So first of all, let's get back to the case study. I need to create the composition of the reservoir fluid. So let me change the active database to the database I just created. To create a compositions, I need to go to the Fluid Management tab and then press Create Fluid. Okay, so now I have a full list of components in here. So because I want to save time, with Hydroflash, I have this option that I can copy and paste a list of compositions to the database. So I just select the names and the mole fractions here, and then I go back to Hydroflash and press this button, paste name and mole fractions, and it just imports all the compositions here, all the components, and with mole fractions. And then I need to add the C7 plus pseudo component. So the name of the pseudo component is C7 plus. It's a plus fraction. The starting number is 7. Molecular weight is 193, and specific gravity is remember 838385. And then the boiling point critical properties now can be calculated, and then I press add component. The mole fraction of the pseudo component was 20.17. I'm sorry. Okay, now the sum of all mole fraction will be 1, which is correct. And then I call this fluid. I give it a name. I can see the properties of the pseudo component SCN6 and C7 plus here, and also binary interaction parameters that I have for this composition. And then I press create. So now, when I create this composition, I can perform calculations. For example, I can perform a PT flash calculation, and it gives me the results of the PT flash at 5 degrees and 50 bar. Okay, so now I want to, first of all, characterize the fluid, because this fluid has not been characterized. So what I need to do is to go to Fluid Management tab again, and then because this component, as you can see, we have VAX in this component. So I press VAX characterization because we have VAX in the composition. Now what I need to do is that I need to enter the PVT information here, also the single flash compositions, flash gas and stabilized oil, and also the VAX content of the fluid, and also the name of the new characterized fluid, because when you characterize a fluid, you need to make a new composition. So I start inputting the composition because I don't want to input one by one mole fractions here. So I have the information in an Excel file. I copy it, and then I come here and I paste it. Oh, sorry, this one. Okay, now it's ready. And then I just need to, the VAX content is 8.9. The GOR is 1327. Flash gas molecular weight is 24.4. Stabilized oil density is 0.6. Molecular weight is 178. And then when all information has been inputted, also you can choose whether how many pseudo components you want to create, you want software to create. But I just let this option to be automatic. So the software itself choose the optimum number of pseudo components, and then I press characterize. Now, as you can see, because I have VAX in the system, the characterized composition has some light components, methane, ethane, propane, and etc. And also these fractions from F6 to F38 plus, and also some normal alkane sort of components based on the VAX content I entered here, as you can see, from N20 to N56 plus. So when the fluid is characterized, you can check the composition, molecular weight, and everything, and then you just change the name. I choose a shorter name, VAX characterized, and then I just save it to database. Now the fluid has been saved on database, and then when the fluid was characterized, because all those pseudo components they don't have well, they have estimated properties. I mean, critical properties which are used in equation of states. But what I need to do is that I tune the model using some experimental data I have. So I need to tune it with saturation properties I have, which, for example, I need to navigate to calculation properties and then go to EOS tuning. And then when I press here, it asks me for pressure. If the pressure is 327, the temperature is 113, and then you can tune the model. As you can see the correction factor to the critical temperature or critical pressure, and correction factor to the asymptotic factor. It didn't change the asymptotic factor. The time and the objective function is very low, so that means that the tuning was successful. So I choose a name, so fluid VAX characterized saturation tuned, and then I accept it and I add it to the database. So and then I can calculate the phase envelope of the calculation. So as you can see, let me enter the saturation properties here. So 3.7. So okay, so this is the graph, and so we have this option in Hydroflash. You can enter points if you have an operation conditions or any experimental data. You can enter the temperature and pressure here, and it shows you the point on the graph. So as you can see, the model has been tuned very well with the experimental data, and now it's ready to use the to this model to perform Hydrate calculations or any other calculations. So, okay, if you go to page 8 of the, so we have done that, we have created the database. This is the phase envelope before tuning, and this is the characterization, this is the tuning, and this is the comparison between tuned and untuned phase envelope. I can calculate, I can calculate the phase envelope of the fluid before tuning. So it asks me whether I want to see the new graph in this graph, or I want a new graph. So because I want to compare them, I ask software to, yes, put the new graph on the same tab as this one. So as you can see, the tuning has improved the predictions, and now the new tuned fluid can predict the saturation properties very well. Okay, so calculate the hydrate phase boundary of the system with and without methanol injection. So water flow rate was 4.4 cubic meter per day. So from the molecular weight of water, we can have, and density of water, we can have the rates, the mass rate of water, which is 4,400 kilogram per day, and the methanol flow rate will be 1,900 kilogram per day. So the resulting methanol concentration is 13.16 weight% in the water phase. Now we can make two compositions, one with condensed water and one with methanol solution. So what I need to do is to just add water to this fluid. Okay, so I go to edit composition because I want to add water. I add water to the system, and then I change the name. I name it fluid and water, and I create a new composition. And then I just need to add also methanol to the system. So as we calculated, the methanol concentration is 30.16. The water will be 69.84. Sum is 100. Then I name it with 30.16 weight% methanol. And then I create a new fluid, and then I can now calculate the hydrate phase boundary of the system. The hydrate phase boundary calculations, you need to go to the calculation tab. It's this button, hydrate dissociation. It asks you the units of the temperature and pressure. And also this feature is automatic structure detection is unique in our software. It gives you the most stable form hydrate in the system. So that means that sometimes you form, depending on the composition and depending on the temperature and pressure conditions, you can form different hydrate structures, structure 1 or structure 2. But sometimes, but this option gives you this, enables you to enable software and gives you the most stable hydrate structure form in the system. So you don't need to calculate the structure 1 and structure 2, then compare them together. So it gives you the most stable structure. And then if you want to perform a point base, so you choose this point, and it gives you the dissociation pressure, the most stable hydrate structure, the composition of all phases at these conditions, dissociation conditions, the composition of the hydrate phase, and also some information, molecular phase fraction, CPCV, and second derivative thermodynamic properties here. And at the bottom of it, you can see the options which was used for this calculation. Or you want to calculate a hydrate line or a hydrate phase boundary, which you use this option, this checkbox. And so for this case, I want to know the hydrate phase boundary between 1 bar or maybe 2 bar, and then until 30 bar, 30 bar, with intervals of 5 bars. For this composition, first fluid and water. So this is the hydrate phase boundary, and then I change to methanol, and then I calculate it again. And yes, at this, okay. So now you can see the red graph, the red hydrate phase boundary is the hydrate phase boundary when methanol is present in the system. And the blue one is there is no methanol in the system. As you can see, methanol shifts the hydrate phase boundary to the left side of the PT diagram, which means that the hydrates are less stable when methanol are less stable at these conditions when methanol is in the actual system, and methanol can inhibit hydrate formation. So as is shown in the figure, as if you go to page 9, in the figure, injection of methanol will shift the hydrate phase boundary of the system to the left side of the PT diagram, and it performs hydrate inhibition for around 15 degrees. Now we need to investigate whether depressurization of downstream of the pipeline will dissociate all form hydrates and unblock the pipeline. So to do this, first we need to perform a PT flash calculation and create a new composition. Because when you depressurize the pipeline, some gas will be released from oil and the composition will be changed. So what we need to do is to perform a flash calculation at the pipeline conditions, and then calculate the new composition of oil to this. So I've done this before.
What I want to add to the point you mentioned is that, because they initially thought it's hydrate problem, so they were doing depressurization, because depressurization is very effective technique for removing hydrate. Clearly, they were not thinking of wax problem, because depressurization does not do much about wax. So, so if they do depressurization and the problem is hydrate, and clearly they were sure it is hydrate because they were not sure that the basically pump or methanol injection is working. So they did depressurization and the blockage was not removed. Because the blockage was not removed, now we need to check whether hydrate will be stable at very low temperature. For this reason, we need to calculate the composition of the oil after losing the gas, after the pressure dropping to seabed condition. That is the pressure on the surface, whatever is pressure in surface, and then take into account the hydrostatic head. So that will be the maximum pressure of the pipeline. We know temperature of the pipeline, so together we can calculate the new operating condition, that is the new condition in the pipeline. And then we check whether this condition is inside hydrate stability zone or not. Obviously, that will also change the fluid composition, and that's what we are doing at the moment. That is depressurizing the pipeline to atmospheric on the surface, and then calculating the pressure at subsea condition, and then flashing the oil at that condition, then calculating the hydrate stability zone of the remaining fluid without methanol. Thank you.
Okay, thank you, Bahman. So as Bahman said, so the seabed temperature was 5 degrees, and they taking into account the hydrostatic pressure of the pipeline, which is 20, we can flash and see how much will be the composition of the oil inside the pipeline, and then create a new composition using this the oil composition, and add water to it and see how much would be the hydrate dissociation pressure of this one. So what I need to do is to add this one, create a new composition. First of all, I need to copy this one, and then go activate this one and paste it here, and then add water to it. And I call this one, for example, black, the oil, let's call it just oil, plus water. And then I create a new composition, and I perform hydrate calculation for this range. Yes. So this is the hydrate dissociation line when there is only water in the system. So I need to add methanol as well to see how much will be the difference, because we had methanol in the system as well. So methanol again, and then 13.16, 69.80. Just not sure how much will be the, okay, 1684. That's 100, and then I change the name plus 13.16 weight% methanol, and create a new composition, and then perform the hydrate phase boundary again. So these are straight lines when it's straight after the bubble point. These are the hydrate phase boundaries when after depressurizations, and these are the hydrate phase boundaries when there are gas, reservoir fluid, and water or methanol. So let's get back to the figure here, figure 11. So as you can see, we are showing here that depressurization, if we assume that there is no methanol and pump didn't work properly, if we assume that methanol wasn't injected to the system, the depressurization after in 20 bar, which we did the flash calculation, we are still in the hydrate phase boundary. So depressurization probably cannot resolve the blockage. Bama, do you want to talk about this section?
Yeah. Here, as Ramin mentioned, the hydrate phase boundary for the original oil with gas is plotted without methanol and with methanol. You see that here, the green line, you see that if there is enough methanol, hydrate should not form. Okay, so now assume we don't have methanol because they were not sure methanol pump was working. So at pipeline condition, hydrate can form. Now you see different point on depressurization, and then when you pressurize the fluid will be flash in a way at that temperature. Now the gas will migrate out of the pipeline, will move out of the pipeline. So the remaining oil, we can basically flash the oil at depressurization condition and calculate the remaining oil composition. Now this oil, which has a lot of heavy component, then the hydrate phase boundary of that oil without methanol is plotted here. You see that in the two-phase region is the same. When it goes above bubble point is a near vertical line. And with methanol, it goes further to lower temperature. But you see that some point, despite depressurization, some point are still in the hydrate stability. Now, this means that there is a very small possibility of blaming hydrate as a problem. The reason is that if hydrate form, it will change the composition and we take away a strong hydrate forming compound. So when we depressurize, some hydrate will dissociate, and in most cases, the fluid can be mobilized. The fact that the blockage remains after depressurization means that the source of problem is less likely to be hydrate. However, because that was the instruction we got from client, we continue investigating possibility of hydrate. But we know that this is not hydrate because as I said, a large part of the hydrate should have been dissociated, and very small amount of hydrate is possible to remain if methanol pump is not working. Okay?
Okay, thank you. Right. So what we did in the first section was that we calculated, we wanted to know whether the depressurization will resolve the blockage. So what we did is that we entered the fluid compositions, we calculated the phase envelopes, we calculated the hydrate phase boundaries, and then after depressurizations, we calculate the composition within the pipeline, and then perform the hydrate phase boundary calculations again. And then with knowing the pressure inside the pipeline after depressurizations, we concluded that probably the depressurization didn't resolve the blockage problem. So do you have any question up to this point? If you have any question, you can either write to me or you can Just unmute yourself and let us know your question. No question? Was it that boring? Okay.
No,
Michael,
Rami,
yes. Yes.
you explain very well, okay?
Okay, yeah. I can, Michael, you had your hand right. Do you have a question? Okay. Well.
Sorry, Ramin, I had a bit of trouble unmuting there.
All right.
Sorry, good morning. Thank you very much for this presentation, by the way. I just, it's really more of an observation than a question, I think. When we're talking about a remediation situation where we already have a hydrate, it might be because of insufficient dosing or for whatever reason, we then have a problem that when we start our pumps, we can't really assume a constant mixture of methanol and water content. So at the point of injection, you get a high concentration, and that will then be removed through the fluid to create this raising of the hydrate, the phase boundary. But my question is really is, do you have any means of modeling like a variable composition of methanol emanating from an injection point?
Well, that's a great question. Well, actually, in our software, because we deal with static conditions, so that means that we need to know the composition, and it's equilibrium conditions. So we assume infinite time. So because the location and the dynamo, what happens in the flow of the pipeline, we don't calculate that. So it's just one point, the thermodynamic and the equilibrium conditions. So what we give you, you need to know, for example, if you have a pipeline, you have this injection point, you have your pump in location 1, and then you want to know what would be the differences in the dissociation point through the pipeline, because the methanol is injecting, and you have this gradient of concentration of methanol inside the pipeline. So we need to know, you need to enter point by point, knowing what would be what is the concentration of methanol in each section of the software. So in each section of the pipeline. So the software doesn't tell you what would be the composition of the methanol through that section of the pipeline. You just need to enter that composition yourself. Did I answer your question?
Yeah, that does. Thank you. That makes that.
Okay.
Can I add one?
Sure, Bahman, yes.
Yeah, it's a great question. I should tell you from design perspective, when you are designing amount of methanol, how much methanol they need, they assume 3 to 5 degree safety margin. Yeah. And then they assume non-equilibrium distribution of methanol. So they add a percentage for that, okay? So for example, if the methanol concentration required for this inhibition is, 20%, they consider normally 3, some countries 5, but normally 3 degree of safety margin. And then they assume a percentage of inhibitor they add because of bad distribution. Now, the fact that they inject methanol at the wellhead, the wellhead temperature is much higher than hydrated stability zone. So hydrate is not forming. Depending on the pipeline, this pipeline, maybe the fluid we travel 5 kilometers, 10 kilometers, depending on the insulation performance, until it reach hydrate stability zone. By that time, the fluid should be well mixed. But if it's not mixed, it is good news. The reason it is good news for methanol, because methanol is lighter than water. So methanol will stay above water and prevent hydrate formation at the interface, which is more important. So, but the situation would be reversed for MEG. For MEG, if it is not mixed properly, MEG will stay at the bottom of the water phase. So, an interface is the worst place for hydrate formation. The reason is that hydrate needs around 15% gas, while the gas dissolved in water is less than 0.1%. So interface is where the gas get into water and form hydrate. So the fact that methanol is lighter than water, and if it's not properly mixed, is to our benefit. Did I manage to pass my message here?
Yeah, thank you. That's why I preface my comment with in a known hydrate situation where you are remediating. In other words, you'll maybe go in subsea with a vehicle to inject methanol into a point, into an access point that doesn't normally have methanol delivered. But I'll take your point about the mixing and the phase boundary between the fluid interfaces. Thank you.
If it is a vertical well, vertical condition, is not, methanol is not as efficient as MEG, because after melting hydrate, methanol comes on at the top of the water and loses contact with the hydrate. MEG is better, okay? And our research shows that if you use a mixture of MEG and methanol, adjust the density to near water density, it will be the best efficient procedure for melting hydrate in a vertical line. It could be the wellbore, it could be riser, yeah. So if you like, we can send you that paper.
Thank you, I'd appreciate that. Thank you, Bahman.
Thank you. Right, thank you, Bahman, as well. Well, any other questions? Okay. So let's move on. Second part. In October '94, 2-kilometer section was replaced, and the redundant section was cut into 8 pieces and were left on the seabed. This time, the operator made sure that methanol injection pump is working properly, and furthermore, the production rate is reduced together with water production. So while methanol injection rate was kept the same as the last year, ensuring that the methanol concentration is high enough to prevent hydrate formation. Second blockage occurred in November 1994. So the operation conditions for this stage of production was are given in this section. Is 189 cubic meter per day, and the water flow rate is 3.2, and the methanol dosage rate is exactly the same, and the pipeline pressure and the seabed temperature are 5 and 100 bar, and normal platform arrival pressure is 20 bar, and the platform temperature is also 10 degrees. So the question is that with injecting enough methanol in the system, what could be the cause of the blockage? So what we did, is that they replaced the pipeline, they reduced the production rate, they kept the methanol dosage rate constant, so that should increase the methanol concentration in the system. So why that blockage happened again? So let's calculate the hydrate phase boundary for this system again, and check the hydrate phase boundaries. So the water flow rate is 3.0 now, which is 3,200 kilogram per day, and the methanol is the same as before. That gives us a new methanol concentration of 37.26 weight%. And then I just need to, let's go back to Hydroflash. I just need to change, sorry, I need to change the active composition of the fluid and water. So what I need to do is to add methanol. And so this time is 37.26, which gives us, how much would it be? 2.74. Yeah, okay. And wash, and then create new, and then I can compare the hydrate phase boundary of the system. I want a new graph, so this is this one, and then raw fluid and water to graph 2. Okay, so at 5 degrees and maximum pipeline pressure, let's see where we are. 100 bar. So you see, if we don't have methanol in the system, the operation conditions is within the hydrated stability zone. But when we have enough methanol, and we are sure now the pump is working properly, so we are outside of the phase boundary of the system when methanol is actually in the system. So what would be the cause of the pluggage? We definitely do not have hydrates here because we are outside of the hydrate phase boundary. So Baman, do you want to add anything here at this point? Baman?
No, I don't have any more comment. Yeah, that's fine.
Okay. Right. Okay. So, so the worst condition is that operational condition falls outside of the hydrate phase boundary of the system. On the other hand, we are sure that enough methanol has been injected to the pipeline. So we are now going to investigate the possibility of asphaltene formation in the pipeline. Although, as shown in table 4, let me go to table 4, beginning of the document. Okay, SAR analysis. So as you can see, some people say they look at the SAR analysis of the system and say, well, the asphaltene concentration in the oil is very low. So the possibility of asphaltene formation will be very low. But this is not the case. But in many studies and also our own observations in the lab, the risk of asphaltene precipitation is not necessarily related to the amount of asphaltene in the data oil or SAR analysis. So, so we cannot really rely on the SAR analysis and say, okay, because the asphaltene concentration is very low, so we don't have any asphaltene problem in the system. We need to investigate that. And to do that, I need to characterize a fluid using this SAR analysis. So let me, okay. So this is the figure 13 in your document. So I just need to go back. Let me change the database. This is a bit more quiet database. Okay. So I need to characterize the fluid for asphaltene calculations. Here I am. I have some features here, the PVT properties, the SAR analysis, the single flash data, and I need to enter them all. So the single flash data, I have it here. I just paste them. Sit here. The GOR is, how much was it? 1327. Flash gas molecular weight is 24.4. Stabilized oil density is 0.6, and stabilized oil molecular weight is 178. The SAR analysis saturates is 69.1, and so 29.03. Resins is at 177. Asphaltene is 0.1. Okay, so now I have everything here, and so the new name for the new fluid is okay, and I just press characterize. So when we characterize asphaltene, we characterize the fluid for asphaltene calculations. So what we do is that we characterize the fluid into light components: methane, ethane, propane, CO2, nitrogen, and then lump some the SAR analysis, the SAR fractions like saturates, resin and aromatics, and asphaltenes, and also heavy gas. So whatever left goes to the heavy gas. And then so we have these components as characterized fluid for asphaltene calculation. So as you know, as soon as the calculation is done, I can add the new fluid to our database. Okay, so again, because this is characterized fluid, we need to tune it, because all these properties of the equation of a state are estimated and they're not reliable. So whatever software gives us after characterization, it's not reliable, because we need to tune, because all these parameters has been estimated using correlations. So what we need to do is that we need to tune the model using at least one set of experimental data, which you usually, for asphaltene calculation, you need to have the upper onset or lower onset or saturation property. So what I need to do is to go to the calculation tab and this button, asphaltene model tuning. And for asphaltene, we use PCSAFT equation of state. PCSAFT equation of state is different from cubic equation of state. PCSAFT it's called a molecular equation, which is it takes into account all these molecular interactions, and it is very good for wax and asphaltene predictions. So in asphaltene model tuning, you have different options. You can tune the model using only AOP, upper onset point, or only saturation, or onset and saturation. And also you can use titration data if you have any titration, normal pentane or normal heptane data. And also if you have titration and also upper onset, the measured upper onset using a depressurization method. So in titration, you usually have a concentration, which is the volume of the titrant, which is, for example, in this case, normal heptane. We can change it to normal pentane, and then to the volume of the oil, and then the titration temperature. So, and this volume of the normal titrant is the exact volume that asphaltenes starts to precipitate. But AOP, the depressurization method, gives you can measure the AOP using depressurization method with live oil, and so it gives you a temperature and also an onset pressure or an onset temperature. So because I have, for this case, I have onset saturation properties and AOP, I use this option, and then I enter the properties here. 85. Pressure is 361. This is the upper onset, and saturation property is 113. Saturation pressure is 327, and yeah. Okay, so now you can see tune PCSAFT pure component properties for asphaltenes. which is M, sigma, and epsilon. These are PC-soft parameters, and also the time of the tuning and number of iterations, 200, and the objective function could be reduced to only 1% with respect to the other properties. So what I need to do is that I choose a name for this new tuned Asphaltene model and then add it to our database. So what I did is that I tuned everything here before. So I just go to the course. Close the software by mistake. Okay, so so I have tuned the model using this Asphaltene data before, and I want to calculate the Asphaltene onset pressure and temperature. So as you can see here, if you go to calculation tab and Asphaltene onset, it gives you, if you choose, for example, I choose this fluid, it tells me that fluid is not characterized. So it doesn't let me to start any calculation. And if I choose this one, it says that, okay, fluid is characterized, I can perform calculations, but model is not tuned. So the result, the predictions will be reliable. So what I need to do is just select the tune one. So when the fluid is characterized and also tuned, it gives me 2 red lights, sorry, green lights. And then, so I can calculate a point like hydrates, a point of onset on Asphaltene onset, or a Asphaltene phase boundary, the units. It gives me this option whether I want to use the upper onset, which means the above bubble line, or below bubble line Asphaltene onset. So I want to know how much would be the Asphaltene phase boundary between 5 and, for example, 400 degrees, and then I press run. It's 400 points, so it takes a bit of time. Okay, so this is the upper phase boundary, and now I want to calculate how much would be the lower phase boundary of Asphaltene. I just use this to -40, and probably 100 is enough. Okay, so this is the upper phase boundary and this is the lower phase boundary. So I just need to calculate the bubble line of the system. I go to bubble temperature because I have tuned this with saturation properties. So I choose the saturation tuned, and pressure I ask between -30 to, for example, 200 degrees. Oh, sorry. Bubble. Okay. -30 to 200. Okay, and this is the bubble line. So, okay, so now we have upper Asphaltene phase boundary, lower one below the bubble line, and this is the bubble line. So let's see where we are in this PT diagram at 5 degrees and 100 bar. Okay, so we are here. We are actually outside of the Hydrate Asphaltene phase boundary, because as you can see, the Asphaltene at this section, these are the Asphaltene is not stable, this section, but in this section, Asphaltene is stable. So it means that at this condition, Asphaltenes are not stable. So that tells us that probably that definitely actually the blockage wasn't because of the asphaltene in the pipeline. So Hydrate wasn't an issue, and now we concluded that asphaltene is not the issue as well. So Bahama, do you want to add anything at this point?
Basically, we knew the asphaltene is not a problem. We presented here just to make the course more exciting.
Yes.
So
I wish you didn't say that, Bahama.
Okay. So we knew that, but we did that calculation to demonstrate that, you know, it is a good practice to test all possibility, okay? But you can see that even if asphaltene was a problem, by depressurization, we go further away from asphaltene phase boundary. So, you know, asphaltene is not enough asphaltene formation that can block the pipeline. So enjoy the rest of the course.
Okay. So I would suggest a 10 minutes break if you want, and then we can come back in 10 minutes, and so we can continue the course. Is that okay with everyone?
Yeah, that's okay. Thank you.
Okay, great. So we'll come back in 10 minutes. So that at UK time, now it's 10:07, so we'll come back at 10:17.
Again. So next week, we start with Yuan. This is training 4, and then it will be repeated again in the 4th week. And then we stay quiet for around 6 months, generate more training material, and start again within 6 months. Please inform your colleagues. These are completely free.
Okay, thank you, Matt. So is there any more questions or okay, so okay.
No, just to say, Raman, I am interested in getting more information about the software, and
Sure.
and also participating in other events that you'll be holding. So
great. So yeah, I'll keep you updated about the next you know, our sessions for this for the course. I'll send you joining detail on course materials, and I'll also send you a trial you know, of the software, so you can have it and test it and evaluate whether it's something that you're interested or not.
thank you very much.
You're welcome. So I would like to thank you all for attending and your patience and your interest. So as Bahman mentioned, we will have this course for another 4 weeks with different case studies, hydrates, vags, and asphaltenes. And so we can let your colleagues, your friends know this is completely free, and they can join us whenever they want. And also I have recorded this course, and we send you the video. You know, I think at most on Monday, and then so yeah, please let me know. You have my email address. Also, if you have any general queries, please send us an email at to the email address hydroflash@hydrafact.com, and I will be happy to help. So thank you again all. Bahman, do you want to say anything?
Yeah, I just want to thank you, everybody, for taking time from work and joining us, especially Robert has asked some question, and thank you very much, and hope to see you next week.
Okay, so see you all next week. Thank you.
Thank you very much.
Thank you. Bye.